guys, this is Professor Janacek, and I want to talk about an application of derivatives. Let's look at rates of change. There's an average rate of change and an instantaneous rate of change. The average rate of change is the rate of change over a period of time. The instantaneous rate of change is at a single moment in time. So there are two contexts in which we can look at rate of change. One is motion, and this is specifically one-dimensional motion. If we let time be the variable t, then the position function, the position at any time, is a function of t. We'll call that position s. The initial position we often denote as s subscript 0, and that is simply the s function evaluated at 0. Displacement, how much it changes from beginning to end, we use the notation Greek letter delta, s. Delta typically means this uppercase delta symbol typically means change in, and that is simply the position at time 2 minus the position at time 1. Now we have velocity. There are two types of velocity. First off, velocity in general is the change in position divided by the change in time. So this is our first rate of change. It is the rate of change of position with respect to time. Now there are a couple of types of velocity. We have an average velocity, which we'll denote as v subscript AVE. It is a function of time as well, and it is s of t1 minus s of t2, so that's the displacement of our position, divided by t2 minus t1. This looks very much like the formula for slope, and that's exactly what it is. We also have an instantaneous velocity. That is denoted just v of t, and that is ds dt, which is s prime of t. And speed is simply the absolute value of the velocity, the instantaneous velocity. Acceleration is the change in velocity over the change in time. So this is another rate of change. It's the rate of change of velocity with respect to time. We'll denote acceleration as lowercase a. It is also a function of t. And it turns out the acceleration is the derivative of velocity. So it's d dt of the velocity function. But remember, the velocity function is the derivative of the position function. So we're looking at the second derivative of the position function. So if we have a position function s, the velocity is the first derivative and the acceleration is the second derivative. Right. In the business world, we have a similar application. We can look at the rate of change of the cost. So suppose we have the number of items, we'll call that x. And suppose we have a cost function, c of x. Again, this is the cost in terms of the number of items. So cost is a function of the number of items. Now we have an average cost, which is denoted c bar of x. So anytime you put a bar over a variable, it means that you're typically looking at the average. To determine the average cost, it's the cost function, c of x, divided by x. Now this is the cost to produce an item. right? What we expect to produce, how much it'll cost to produce just one item, again, on average. Now, the marginal cost, you'll never guess what this is. This is C prime of X. And the marginal cost is the cost to produce one additional item. So this is after we've already gone through kind of the startup cost and everything's taken care of. How much will it cost me to produce one more item? So the cost function, the average cost function, really is kind of talking about in terms of what's going on currently. Whereas the marginal cost is really talking about what's going on in the future. What will the cost be in the future? Let's take a look at an example here. Suppose the cost to produce X items is given by the function c of X, which is equal to negative 200ths x squared plus 50x plus 100 for x between 0 and 1,000 inclusively. We want to first determine the average and marginal cost functions. Okay, that's not so bad. The average cost is simply going to be c bar, which is c of x divided by x. In this case, that's negative 200ths x squared plus 50x plus 100 over x, which simplifies to negative 200ths x plus 50 plus 100 over x. All right, well, there's our average cost. Let's take a look at the marginal cost. This one is simply c prime. So all we have to do is take our c function and find its derivative. Well, that would give us negative 400ths x plus 50. So there we go. There's the average and marginal cost functions. Now, let us determine and interpret the average and marginal cost for the first 100 items. So what's going on here? Well, in this case, we want to evaluate this at 100. So c bar of 100, well, that's negative 200ths times 100 plus 50 plus 100 over 100. Take a moment, do those computations. You shouldn't need a calculator for that. 200ths times 100, that should be easy. Add 50, and then add, we'll add 1 there at the end. So it looks like we should end up with 49. All right, so our average cost is 49. What does that mean? The average cost of producing the first 100 items is $49 per item. And now I realize we weren't told this is in dollars. It would be whatever the units that were given. We'll assume for this situation that it's going to be in dollars. All right, so the average cost of producing the first 100 items is $49 per item. Now let's take a look at the marginal cost. The marginal cost at 100, that's negative 400ths times 100 plus 50. Well, that gives us 46. Again, make sure you can do this computation without a calculator. So this means that we're going to This gives us the cost of producing one additional item after we've already produced 100 items. So that means the 101st item is $46. So make sure you understand the difference. The average cost is going to be the cost per item for the first X items, but the marginal cost is one more after that. All right, enjoy.